Hi everybody, my name is Brian.
My name is Daryl, and today we'll be going through our EE4455 LabVIEW project. This will be a quick introduction of our project. Our project consists of 4 unique functions. First will be the user is able to light up individual LEDs and also display an array of patterns that we have programmed onto the board. Second function will be the water flowing program, where users are able to pick up the board, move the board around to simulate water flowing on a flat plane. The third function will be the audio detector. This program takes in audio via this audio sensor and also it will display the amplitude of the audio via the LEDs. Last but not least will be our main function of our project, which is the Morse code translator and transmitter. This project takes in a word input from the user, translate it into Morse code and transmit it visually through the LEDs. Morse code is made up of a series of dots and dashes, and therefore we display short flashes as dots and longer flashes as dashes. Before we dive into the demonstration of our project, we will first move on to the hardware and look into how we built our project.
Okay, so let's talk about the hardware of our project. So this is what we built. So as you can see, the hardware actually comprises of 2 parts. One being the LED grid itself and the audio sensor, as you see right here. So for the LED grid, as you might notice, the LEDs here are actually quite cloudy. So why is this so? As you can see in this picture that we took, the LED on the left is cloudy or diffused. As you can see, the light is more spread out, or the one on the right is clear with the light being focused at the tip. So diffused LEDs have this glow effect that we wanted, thus we sandpapered all our clear LEDs to get this effect. So the next step was about building the LED grid itself. This is the cardboard template we made to align the LEDs into a grid. And we also connected them in a way such that they share common cathodes. We also soldered copper wires to give more strength to the structure. And lastly, the audio sensor. As you can see, there are 3 wires coming out of it. The first being a 3.3 volt VCC, the ground, and a signal cable. Upon completion of the hardware components of our project, the next step was to learn how to control each of these LEDs individually. Thus, we made a simple program to perform this task. As you can see here, our front panel consists of a grid of LED buttons, and when one of these are clicked, the corresponding LED will light up. This is how the physical wiring looks like of our project. We used up all the I/O pins from sectors A and B of the MyRail, basically from AIO0 to AIO15 and BIO0 to BIO15. Now let's move on to the LabVIEW program itself. So this is our block diagram, and on it you can see that there's this cluster, this purple square here, and this cluster contains all 32 buttons on the front panel. And connected directly to this cluster is an unbundle function. Basically what it does is that it splits back out all 32 boolean variables, and each of these is linked to an LED. So essentially what is going on is that one button is linked to one LED, that's all. And after we got this to work, we decided to move on to a more complex task, which was creating patterns on the grid. So this is our grid patterns program. Please take a moment to have a look. So as you might notice on the front panel, the grid is actually split up into 4 sectors, and I will later explain our purpose for doing so. As you can see here, there's also a knob to control the delay between each pulse. This is how our LabVIEW program looks like. So how the entire thing works is similar to a 7-segment display. For example, to control a 7-segment display, you would need to send a series of 7 bits, like perhaps 1110001. So a 1 will light up a segment and a 0 will turn off a segment. And this is exactly the same way we constructed this program. So the first 3 sectors represent a 9-segment display, and the last sector represents a 5-segment display. And why we structured the program this way was because we couldn't get the Boolean array constructed here to take more than 9 bits at a time. Thus we had to split them up like so. And the arrays here contain decimal numbers that will be converted into a binary sequence that will be fed to the LEDs. And this is a very, very long array.
Demonstration of the water flowing program. This is an interactive program whereby the user can pick up the board, move and tilt the board to simulate the flowing of water on a flat plane. As you can see, when we tilt the board, the LED display represents the water on a flat plane flowing to the respective direction. The number of LEDs lighted up in a direction so as to represent water flowing in that particular direction will be determined by thresholds. This will be explained in more detail later. If we were to move the board really fast in a circular motion, we can see that this replicates water being thrown away towards the outer edges due to its centrifugal force. This program truly mimics the physics of water flowing on a flat plane with an external force applied to it. So how did we program this? First, we had to divide the LEDs into sections based on the output amplitude of the accelerometer. For this program, we will only be taking output from the X and Y axis. From this figure, we can see that the LEDs are grouped in a way that they must hit a certain threshold amplitude for the respective axis in order for it to be lighted up. Based on this orientation of our board, where the wires are on top, we can see that the X-axis runs through vertically, while the Y-axis runs through horizontally. And each individual LED has a specific condition to fulfill for it to be lighted up. Take this particular LED for example. The condition for this LED to light up is Y more than, while the next LED to the right is 2 times more than. These symbols means that if 1 more than, the value has to be more than 0.25, and 2 more than, the value has to be more than 0.5. These values comes from the accelerometer. More interestingly is in the 4 quadrants, quadrant 1, 2, 3, 4, you can see that there's an AND gate for two conditions, which means to say that these 2 conditions must be met before this particular LED will light up. So how do we translate all of this into LabVIEW? Let's take a look. So here we can see the accelerometer. We take the X and Y axis output and feed it into comparators, more than and less than. The output of these comparators are then fed into our LEDs. These are LEDs. These represent the positive X axis, negative X axis, negative Y axis, and positive Y axis. And this will represent the quadrants, quadrant 2, 3, 4, and quadrant 1. So these gates on top here are more than and less than, will settle for the vertical and horizontal axis. When we move down here, these are our comparators, more than and less than, followed by the AND gates. These gates will satisfy the condition to light up each individual LED. We can see that each AND gate corresponds to a single LED output.
Next up will be our audio detection program. So this is just a demonstration of it working. There you go.
Multi-silicon sound system. Please disengage all equalization media. Let all wafers flow naturally. All test data will be in cycles, starting from 360 cycles down to 10 cycles. Test will begin in 5, 4, 3, 2, 1.
As we mentioned before, the audio sensor has 3 wires. The VCC here that is connected to 3.3 volts, and on the other side the signal and the ground cable are connected to sector C of the MyRail to A1, 0 plus, and A ground. The input voltage we get from the signal cable of the audio sensor changes with the presence of noise. So we are making use of this change of voltage to detect sound in the environment. So similar to the water flowing program, we are also using a threshold concept to get the LEDs to react to sound. In the previous example that we showed you, the first threshold was set at 1.64. So if the input voltage is any higher than this, the LEDs in that threshold will light up. The second threshold was set at 1.66, the third was set at 1.68, the fourth at 1.7, and the fifth at 1.72. Now let's move on to the program that produces this magic. So the front panel shows an amplitude waveform chart, and on the right of that you can see there are 5 numeric controls that specify the threshold ranges. So users can actually make use of this to actually tweak the sensitivity of the program. And on the right, the block diagram, you can see the LEDs are assigned to their respective thresholds. This is threshold 1. This is threshold 2, 3, 4, and 5. So each of these threshold groups are connected to a greater than or equal to comparator right over here. So the program is comparing the current input voltage to the threshold that the user has set. If the input voltage is greater or equal to that, the comparator will output a true, and that lights up the LEDs in that segment.
And finally, we'll be demonstrating our main function, the Morse code translator and transmitter. So first thing, the user will input a word into the text box and run the program. In this case, we have entered the word cat. The program then translates this word into Morse code and transmit it visually via the LED display. We display a short flash to represent a dot and a longer flash to represent a dash. Let us now watch closely to the display. Long, short, long, short, followed by pause, short, long, pause again, and a long. Okay, let's see if this is correct. Okay, over here on the left, we have the code that was just being transmitted by our device, and on the right is the table of Morse code translations. We can see that dash dot translates to the letter C, and dot dash translates into the letter A, and just a dash translates into the letter T. Therefore, this is correct. So, let us now take a look at the LabVIEW program. We have a total of 5 main modules in this program. First module will be the user input and a validity checker. This checks if the word entered in the input is in the correct format. We use a regular expression checker to check for capital letters that are from A to Z. Once this is valid, the data will be moved to the second module, which will split the word into single letters for translation in the third module. The translation module, which is our third module, will translate each letter into its respective Morse code. The translator gets the information that it needs from this truth table over here. The data then goes into the fourth module that splits the code up in preparation for the transmission of the short and long flashes, which is represented by ones and zeros. The transmission of the code will be the final module of our program, which is over here. If it is a 1, it will execute a short flash. If it is a 0, it will execute a long flash. This is the module where the user will be able to see the flashes. And we have come to the end of our video.
Thank you for listening. We hope you enjoyed it.
Good luck for your examinations.